Alright, so I just wanted to make a couple notes about some of the code. So we're looking at the Python version right now, and the way the Python version is written, I'm I'm getting this from Programming for Computations. Uh, so you can read through this yourself, but I changed a couple of things here, but not too much. Um, I just thought it was interesting what uh, some people will code in and some people don't. Um, so in this case, the multi-dimensional Newton method here takes in the what we're going to be calling our g, and then the gradient of g, which is actually the Jacobian of g, I should say, because g is this function right here is multi-dimensional, right? So this is a system of equations, and so the derivative then is the Jacobian matrix, and then the initial guess, and then your epsilon for a tolerance. And this epsilon is going to be when the y value, or the output, is close to 0. Okay, because that's what we're looking for, right? Okay, so then it just starts off. It estimates, or it takes into account the norm of f instead of the norm of g, or the condition number of g, which I usually check. I think it's a good idea because down here, I don't know if you can see this on line 21. Um, this is where you're solving for the inverse of the Jacobian matrix, and so the solver, the Python's linear algebra solver, does not check, or will just throw an error if your matrix is not invertible. So you do have to be careful in here. Um, in Matlab, I check the condition number to make sure that things aren't getting bad here, which is a good idea. If your solver is if the condition number of the Jacobian is getting too large, then this inverse uh, may have a lot of numerical error, and so you may run into trouble with this algorithm. Okay, so that's just what I wanted to mention. And then here, this is a little bit different way of getting the inverse, right? Which I thought was kind of a cute way to do it. If you take delta to be the term that you're solving for here in line 22, and delta is equal to, um, the inverse of j times f. By the way, the negative sign is inside the, or is grouped with the f for some reason instead of on line 22. Um, yeah, then the delta you could actually solve for um, using the linear algebra. You could. This is one way to do the inversion without actually inverting it. So okay, so that was kind of an interesting way to look at that. Um, let's see. I think the rest of this is pretty straightforward. I do like the way they coded this up. Otherwise, uh, yeah. So our actual function here is from line 9 to line 31, and then line 34 to line 48 is just a test. And so they have quite the function here that they're testing this on. Uh, good. Okay, so then we just run the code here, and then we just run the function that they have, and so it gives us the number of iterations, which is 4 in this case, and then the location of the 0 is 1, 0. Good. Uh, Now for the Matlab version, let me see if I can pop that up here. So for the Matlab version, I'm running this a little bit differently. I've got the function f here that actually returns all 3 functions. So f is returning g, the gradient of g, and the Hessian of g. So my function f is actually the original scalar valued function. In this version, this f is not the scalar valued version. This is the gradient, and j is the Hessian. And actually in Python they want you to do those 2 functions separately, like you see down in the sample. Okay, in the Matlab version, I'm just